And we are recording. All right. So I answered two different questions. So the first one was about the quizzes. Yes. So the quizzes serve as your study guide. So you should take it. To answer your question, she asked how many times you can take it. Unlimited.
Oh, okay.
And your grade that's recorded is your highest grade. So like, let's say you take it the first time, you just ace it and get 100%, but you still want to use you want to do it as a way of studying, just take it as many times as you want. You could get a 0 the next time and your grade is still 100. So yeah, that's why I have it set up that way. Good question. And then to answer your question, labs will always be due on Friday, pre-labs and labs. I did that on purpose too, so hopefully it's just easy to remember. Just all due dates for the most part are on Fridays. I always encourage people to turn it in early. Some people have, and I've already given them the grades back, and now they can fix their mistakes before the due date and get full credit. But yeah, Friday, today, by midnight is the due date for the lab and pre-lab. And if you find yourself close to midnight, be like, oh my God, I still have to turn both of them in, I haven't finished them yet. Prioritize next week's pre-lab over this lab. So this lab's behind us, done it. It's a little bit less important next week. I'll make sure you know what you're getting into. All right, so I started recording early this time because, well, partially because you guys had great questions that I wanted to get on the record, but also because I've been having recording issues, so I thought I'm gonna start it early. So if you're watching the video, go ahead and skip ahead in the video until you see the PowerPoint show up. And I don't mean here, you will see the PowerPoint here, but don't, you can skip ahead until you see the PowerPoint. Actually, let me just give you an example. I'll just pull it up. I need to pull the PowerPoint up. Well, anyway, yeah, so if you're watching the video, scroll ahead until you see me share the PowerPoint on the screen. Not this screen, but when I share my screen and you can see it perfectly, that's when you can stop. Right now, I need to go download this PowerPoint again. Somebody messed it up. What's that? That's enough. So do you have any plans for the weekend?
Do I have plans for the weekend?
Yeah, for the long weekend.
I have on both days 2 12 to 8 shifts. I'm not happy. I am already burnt out from last week and this week.
How you feel? All right, let's run down this again. There we go.
Luckily on Monday I'm not doing anything, so.
Oh, good. Relax, maybe.
Yeah. So,
All right, let's see.
I sent you a guest email again.
Do what?
I sent you a guest email again.
Oh, okay. It's all right.
I don't know why, but it's not like letting us connect to wireless at all.
It's weird. Well, I'll get it here in a second. Let me just download this PowerPoint and get it pulled up. please. Go. Hope this works. Good morning.
Morning.
All right, it's been approved. Boss. Hey, worked, sort of. We've already talked about radioactive isotopes, talked about bonding. Yeah, that's what we left off. And we left off in a really good spot, actually. Pretend like I did that on purpose. Good morning, Bonner. Let's see. Esther Smith is here first. Gives you a little extra credit for that. And that's a red shirt. Yeah, it's a little dark, hard to tell. So a little extra credit for that as well. Remember, everyone deployed, because at this point, most people deployed are probably having a pretty good time in Japan, Australia, Italy, England. Inson's here in red, a little extra credit. Boggs is here. And Harrison is here. Good morning, Wilder. They're all things that you guys will need to know for the exam. You guys would have what you say. Making simple syrup. Prime ingredient in a margarita. I feel like I should bring margaritas in the class one of the days. Studying. Also with a margarita. The word you do not need to know. Don't need to know dielectric property. It's good concept. In other words, you're not getting that one. How many of you guys have seen the movie, man, this is ironic, but I'm not smart enough to remember the name of the movie, because it's a movie about really dumb people. Set in the future. Oh, man.
Is it like dystopian?
Yes.
And like everyone has like a something percent intelligence or whatever?
Yeah, they're really, really dumb. Humans evolved to be really stupid because technology takes care of everything for us.
There's this really smart dude.
Yeah,
Like,
well, he's like he's about as smart as we are, you know. Luke Wilson plays the character. What's the name of that movie? Anyway, that reminded me of it because there's a part, the guy who's the president, they've been feeding plants electrolytes because humans need electrolytes, so they thought plants need them too, and everybody's starving to death because it's killing the plants. No, not electrolytes. Basically, like a version of Gatorade, which has electrolytes in it. But, what is the name of that movie? Anyway, if I remember, I'll tell you.
I only saw a clip of that, but I know what you're.
I recommend watching it.
Yeah.
I mean, it is obviously it's a joke, but it is possible that we could evolve to be dumber. Anyway, that reminded me of that. Interesting, but you don't need to know anything about electricity in this course. Yesterday was his birthday. Fair day. Two terms you do need to know. You learn more. Remember, anion is a positive ion. Cation is a positive ion. Anion is a negative ion. You might have one or two questions about that on the exam, but honestly, after that, we're pretty much done with it. Good. Race, James. Again, this is all interesting, but this is a crash course for chemistry. Like, this is for people who do it actual chemistry. We're not, I mean, we're barely going to talk about electrolytes. Things going on and on. Again, useful, interesting stuff, but not necessarily important for our course. Ironically, right? It's obviously, electrolytes are important for your human body, but this is not an anatomy and physiology course. Good morning, Noah. You do not need to know Avogadro's number either. Not in this class. Excuse me. Something else you need to know. Boy. Ellis? Grace. Yeah. Grace for the venture. Makes you ready. Wait. Ellis? Oh, okay, I said it. You just didn't hear me. Glad I wasn't going crazy. I didn't. That's not. I guess it's really not good. Whether I'll shoot the question and then if I can answer quickly as well, otherwise I just there and ask. That's right. Whatever. So yeah, this is all stuff that you don't need to know. I've never seen this video, so I'm previewing it to see if I was going to share it with you guys. Give extra credit for answering some questions. I still might, because the beginning part was very useful. It's hard work and are useless. Good. Yeah, you would need make sure you have a title. So like figure one, write the word figure one. Title. And you would never put points in this, but technically the height should necessarily be there. We did metrics, so then we clearly just capital. Not tall, short. No one would ever do that.
Part is zero, right?
Great question too. Yeah, it doesn't matter. Especially since I did the change of the table of the variance. I'm only looking for everybody that's the averages at the bottom. And so far, the one person's got wrong average.
Well, thank you so much.
All right, well, guess I'll stop that. I'm running out of time. It shows my little viewing history a little bit. I'm glad I don't watch anything embarrassing. All right, let's do some attendance. Since we have a little bit less than a minute left. Aki, not here. Blount is not here. Boggs is here. Bonner is online. Clay is not here. Clayton is not here. Dawson is not here. Ellis is here. Paula won't be here. Wait, yeah, I remember correctly. She won't be here. She's definitely not here. Green is here in red. Metallic shirt. Harrison's here. Henson's here. James is here. Kesterson is here. King is online. Lewis is not here. Linda Q is not here. Morrison is not here. Grace is here. Rice is not here. Ward is here in red. Wilcox is not here. Wilder is online. Hey, Parks is not here. Wilcox just came in. It's 8. We're already recording. Let me do some reminders before we get going. Off the top of my head, so far only 2 people have turned in independent work. Really recommend starting it. If for those of you who have done it, you know why. Because it's not as simple as you think. It's not just turning in something. I'm probably going to find something wrong and ask you to get back to me with this, that, or the other thing. So please turn in some independent work. And one person, and this is a good time for me to remind all of you, since this just happened to somebody, I usually run your stuff through an AI detector. And the one person came back like mostly written by AI. I don't believe it because I test the AI detector. I'll write papers and run it through the AI detector and it says, yep, that was written by AI. No, it wasn't. Anyway, but I do it. I do check it through an AI detector. And if it does come back that it says that it was most likely written by AI, then I get really, really picky. Just to be fair, right? So I know I've already said before, every single fact that you have needs to include a source. And you need to have at least one non-textbook source for each paper you write. The one that's, like I said, when it comes back positive for AI, then I'm really, really picky. So make sure when you're writing a paper, you get your sources right. So if you're using multiple sources, make sure that, you know, if you say, according to my first source, blah, 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 make sure that was on the first source and not the second. What else? I think that's it. Also, and again, what I'm getting at here is don't take it personal. I don't think you used AI. The AI detector does. So I'm just being picky. It's good practice anyway, right? Whenever you write something and you say, according to this source, this is the case, you know, it's good to make sure that it's accurate. Especially depending on what you do later in life, you know. Somebody might, depending on your job, that could be really dangerous if you misquote the source. Dawson, right? Lewis, sorry. Lewis is here. Now we can start. I was just waiting on Lewis to get there. Didn't want to start without you. All right, anyway, any questions about stuff in general before we get started? This is great. We finished at a great spot last Wednesday. Oh yeah, sorry. So the first word for attendance is pink, like the color pink. Yeah, so as usual, for those of you in person, you can send me an email at the end and get a little extra credit. For those of you online or watching the video, send me those words. And if you're watching the video as opposed to watching the live stream, then send me a picture of something pink. Whatever it is, find something pink and send it to me. Anyway, so this is where we left off. And like I said, last thing I said about this is you do not need to know this. There's no need to study this graphic, which by the way is not in your textbook. But if you were to study this graphic, the one thing you do need to know, just to remind you, is the big four. What are the big four? Oxygen, hydrogen, carbon, and nitrogen. You don't even need to know that it's mostly oxygen, followed by carbon, followed by hydrogen, followed by nitrogen. You don't even need to know that. And you certainly don't need to know the percentages. Any questions? All right, so that was the end of section 2.1. Now we're going to get into section 2.2, which is all about water. And I know this is hard to read. I'm sorry. One morning I'll be awake enough to remember to fix this. So let me tell you what the learning objectives are. All right, actually there's only one learning objective for this. By the end of this section, you will be able to describe the properties of water that are critical to maintaining life. Life is important, right? So that's what we're going to talk about. As a matter of fact, life as we know it began in water, and it evolved there for about 3 billion years before it came to land. So for that's a long time, 3 billion years. All of life was in water, right? There was no land or life on land, right? That's not let me put it next to that. You don't need to know that. But obviously that makes sense then, right? Obviously water is important to life if that's where life started and where it stayed for 3 billion years. That'd be an interesting independent work topic if you want to look into it. What was the first life to come on land, right? So if I said life was been, in the water for 3 billion years, well, what was the first to come on land? It's really interesting stuff, I think. For example, sharks have been around longer than flowers. Flowering plants came way after sharks. So interesting things like that. Anyway, that's all stuff you don't need to know. Life is obviously still tied to water, which is why, and when we first started this course, we looked at the chapter 1, there's a picture of the Mars rover. We talked about, what's it looking for? And the Mars rover was probably, amongst other things, looking for water. Because if there was water on Mars, which we discovered that there used to be, then there could be, technically it could be life. Here's one thing you definitely need to know though. You know this from the exam. Bullet point right here. Your cells are about 70 to 95% water. You need to know that. That's a big range, but of course that's because it depends on how hydrated you are, which particular cell you're talking about, whether you're talking about a kidney cell or a blood cell. But yeah, that's a number you need to know. Yeah. Also, by the way, that's the average human cell, 70 to 95%. If you want to look it up, well, first of all, you can get deeper in that for independent work. What about the different types of cells? What about a kidney cell versus a blood cell, for example? You can look that up for independent work. Or you could look up, what about other organisms other than humans? What about chimpanzees? What about bacteria? What about certain types of mushrooms? Anyway, the abundance of water is a major reason that Earth is habitable, right? So without water, Earth wouldn't look like it does. Sure. Anyway, let's talk about all this stuff. This is a good introduction. Let's dive into it. As you remember from, hopefully remember from Wednesday, we talked about how water is polar, right? I'm going to do a horrible job of trying to draw it. We got that one oxygen. It's bonded to that one hydrogen, bonded to this other hydrogen. And we know, because oxygen loves to suck those electrons towards it because it has so many protons, we know that the oxygen end is slightly negative and the hydrogen ends are slightly positive, right? You definitely need to know that, so that's what I'm reminding you. That's what makes it a polar molecule. By the way, that's the wrong symbol, that you need to know that, but if you were trying to draw that correctly, there's a little symbol that you would put next to the negatives and positive that indicate that it's slightly negative and slightly positive, but that's okay for this. For this course, we won't worry about it. And because I hate drawing with a mouse, so I'm definitely not going to worry about it. Anyway, yes, water is polar. And its polarity explains most of the things I'm about to teach you. These four things are what we are about to talk about in greater detail. We're going to talk about the cohesive nature of water. You don't need to write any of this down because we're going to talk again. We're going to talk about each one of them in more detail. The other property is its ability to moderate temperature. That's a big one. We'll talk a lot about that. If you've had my Bio 108 class, you should be slightly familiar with that one already. We're going to talk about the biological significance of ice floating. And we all know that ice floats, but I don't know if you knew that it actually has an impact on life. And then finally, the versatility of water as a solvent. Technically, you don't know what a solvent is yet. I haven't taught you what a solvent is yet, but I will. There we go. Let's talk about that cohesion of water. Water molecules stick together due to the hydrogen bonding, right? So remember, like I said, it's polar molecules, right? And that was the last of the bonds that we talked about was hydrogen bonding. And the way I describe it, it's almost like an ionic bond, but a lot weaker, right? Because an ionic bond, if you remember, you have a positive ion and a negative ion, and they are very closely attracted to each other. And remember, a hydrogen bond, you've got a slightly negative thing, a slightly positive thing, and they're slightly attracted to each other. That's hydrogen bonding. So that's why water molecules stick together, and they really do a great job of sticking together. And we call that cohesion. That's a word you might need to know for the exam, cohesion. It's a word I will use throughout the semester, so it's definitely important for that reason. Cohesion is when molecules of the same kind stick together. And what we're getting at here is cohesion is stronger for water than most other liquids. Without getting too deep into it, that's why when you rub alcohol on your skin, it feels cool. Because what's happening is it's evaporating very quickly. And another word for evaporate is basically boil. It's boiling off your skin because it doesn't have such cohesion. It doesn't have the cohesion that water has. So those bonds, they're not sticking together. So they're more easily able to escape off your skin. That's what that leaves that cool feeling about it. That's cohesion. Water is very cohesive. Just so you know, and I'm not going to ask you this, but when something is adhesive, that's when it's molecules of different kinds sticking together. So if I stick a sticky note on the wall, it's adhered to the wall, right? That's adhesive. Those are two different things sticking together. But yeah, you need to know what cohesion is. You need to know that water is very cohesive, more than most liquids. And that's another good independent work topic if you want to look into it. how much more cohesive is it than other liquids? What about other liquids? What about isopropyl alcohol or hydrogen peroxide, whatever? Think of a liquid if you want, and look it up. How cohesive is it? Anyway, why is that important for life? There's a lot of reasons, but the one great example is trees. Trees depend on that cohesive nature of water to be able to transport water up to the leaves. Let's take a look. This picture's not from your textbook, it's from the old textbook. But think about that, especially really big trees. Think about how water gets up to the very tippy top leaf. Like, how's that happen? There's no pumps. It's not like we're pumping water against gravity. But what happens is the water is in there, right? There's water from the very top all the way down to the trunk. The whole thing has water. And what happens is some of it evaporates and it leaves the leaves. But that water that's evaporating is still cohesive, right? It's still attached to the water that's left behind. So as one leaves, it just pulls the rest with it, like a big chain. That make sense? Okay. I'm not going to go into that much detail, but for the exam, you need to know the cohesive nature of water is one of the important factors of water. And a good example of that is trees, right? Any questions about the cohesive nature of water? Well, let's talk a little bit more about it, but any questions about this tree? All right. Then we have something called surface tension. It's the measure of difficulty in stretching/breaking the surface of the liquid. Again, because it's so cohesive, it has very strong surface tension. For some organisms, that's very useful, like that spider that's literally walking on water. It's not floating. Floating is like when you break the surface of the water, but you're less dense than the water. So therefore, you float for that reason. Surface tension is when you're just not even breaking the surface of the water, right? It's all about those hydrogen bonds. That's what gives it that high surface tension. And again, another decent independent work topic if you want to look into it. What about other liquids? What is their surface tension? How do we measure surface tension? Is there a word for it? Like when we measure spiciness, we call it the Scoville unit, for example, right? So is there something that we measure surface tension with? Also, you could look up what kind of organisms rely on surface tension. Anyway, any questions about that? All right, I've been doing this for so long. This picture is from the Olympics, but not the ones in France, not the ones before that, but the one before that. That's how old this picture is and how old I am. But anyway, that's a great picture. Excuse me, make sure that's not important. Anyway, this is a great example of surface tension, right? So what you see here, this is the water line right here, and this swimmer is just coming up. So even though it's kind of above the water line, the surface tension hasn't broke yet, so he's still basically underwater. Anyway, there's another picture of surface tension. I found that on the internet, so I wanted to share it. It's our mascot. And it's a neat looking picture, I think. Anyway, any questions about the cohesive nature of water? We're done talking about that now. We're going to move on to the next one. All right, the next one, in my opinion, is a little bit more important than the surface tension. The cohesive nature of water. It's how water moderates temperature. This is really important. Not just because it's moderating temperature, but because I'm going to teach you some concepts that you're really going to need to know for this semester. Not just temperature stuff, or not just water, excuse me. For example, what is temperature? You need to know this. Temperature is the measure of the motion of molecules. So really, when I say I'm going to go turn the thermostat down so it's cooler in here, I'm lowering the temperature. What I'm really saying, what's really happening is the molecules in the air are moving around slower if I'm lowering the temperature. When I boil water, what I'm really doing is making the molecules move around faster. Make sense? All right. Because of these hydrogen bonds and the fact that these things are bonded to each other, water has a stronger resistance to temperature change than most other substances. So imagine, if you will, if we all stood up. I'm not going to do this, but if we all stood up and held hands. Right, we're all holding hands with each other. And I'm like, all right, let's raise the temperature. By that, I mean, let's move around, right? So then I just ask you guys, let's move around as much as you can, right? So you're trying, maybe you get in good teamwork, maybe get a good circle going, you're holding hands, you're going this way everywhere you can, as much as you can when you're holding hands, but you still can only move a little bit, right? Because you're holding hands. But if you move around strong enough or long enough, and if you are strong enough, you can break the bonds and stop holding people's hands, then you can really move around, right? You'd be twirling and doing somersaults and break dancing on the floor if you're into the Olympics, right? All that stuff. And that's what water does, right? So when you start heating water, it is moving faster. It will raise the temperature, but very slowly. Because the waters are holding hands with each other, so to speak, right? The water molecules are holding hands with each other. So they're trying to move, and they're moving around a little bit. But it takes a lot of energy for it to finally break loose, and then the water start really getting hot. And that's really important. Without that, life would be too hot in some places on Earth. Well, some places are too hot. Like Death Valley, for example, very little water, right? But also, without that, some places would be too cold. And I'll give you an example in a few other slides. But anyway, you definitely need to know that. You need to know basically what temperature is, because that will be important later when we start talking about enzymes and DNA and stuff like that. It'll be important to remember this. That when the temperature increases, molecules are moving faster. But again, this is why water is so great at moderating temperatures. Have you ever seen somebody have they keep a tea kettle on their stove and they put it on the eye when they're done cooking? You guys ever seen anybody do that? We do that. Well, there's two reasons. One, obviously you just don't want somebody putting their hand on the hot eye and burning their hand. But also, it helps cool things off, especially if it's summertime. You're running the AC. You don't want heat energy just pumping off into your air, heating your hair that you're trying to cool, right? So you put the tea kettle on there, and it absorbs that energy without it changing much energy, right? So it'll absorb the energy. Or, let's see, today's a Friday, long weekend. Oh yeah, remember, don't come to class on Monday. No one's gonna be here. But anyway, it's a long weekend. Let's say you go home today, crack open a beer. It's not that cold. Like, all right, I better cool the next one down a little bit better. You're better off putting it in cold water than putting it in the freezer. Because that water is gonna cool it off quicker than the cold air. Even though the air is colder in the freezer, that water is gonna cool it off better. So you will be tested on how to cool a beer quickly. Just kidding, I won't test you. You would definitely get extra credit if somehow you brought me a cold beer. Not on campus, it's against the rules. Anyway, again, water moderates temperatures. Because of this, temperatures stay within the limits that permit life, like I've talked about, right? And the way it does that is, like when we're talking about the atmosphere, it stores the heat from the sun in the warm periods, like during the day, and then gives it off in the cold periods. This is why, if you look at, oh man, I wish I had the picture. Maybe I did. I think I saved it. I'm gonna have to email this to you guys. Technology was better, I would just put it up there. But I found a picture. My brother lives in Seattle, so I watched the news there. Anyway, I was looking at their weather. Where is it? Anyway, I was looking at the weather, and Seattle was like 80-something degrees. And then right over the mountains, not too far from it, it was 102 degrees. Because Seattle is so close to the water, and that water is absorbing all that heat. Meanwhile, on the other side of the mountain, it's very dry. So even though it's same latitude, right? Latitude is north to south. Same latitude, it's a lot hotter just right over the mountain because there's no water to absorb all that extra heat, so it's just hot. How many of you have ever been to a desert? Okay, was it hot during the day and cold at night? That's not always the case, but a lot of times, yeah, right? And that's why. Because in the day, there's no water absorbing all that extra heat, so it's just hot. And then at night, there's no water to then release that heat, so it's hot. And then one last example I'll give you, or sort of. Another example I'll give you is, I wish Morrison was here. In Florida, when they're having a freeze warning, which is very rare, they spray their orchards, like the orange trees, they spray them down with water. Because the water acts like a blanket. It'll freeze, which you might think, oh my God, it's frozen, that's bad, right? Frozen, ice, cold, true. But even though it's frozen, the air around it will still get colder, right? So that frozen water might be 32 degrees Celsius, Fahrenheit, 0 degrees Celsius. But as the air gets colder and colder, that ice is still only going to be about 32 degrees Fahrenheit, right? So it is relatively warm. Anyway, one last example. This is really not important for this class as much as it is for Bio 101. But another good example I think of that is, West Virginia is right about here. London's right about here. Look how much of a difference that is from north to south, right? But London's climate is a lot like ours because they're closer to the water. And because water, not that you need to know this, but this is a great example. This water in the equator, it's getting really hot, right? It's getting a lot of sun. It happens to flow this way always. and then it hits that land, has nowhere else to go, so it comes up here. And as it comes up here, or as it's going north, it's losing some of its heat, but even by the time it gets up here, it's still pretty warm, which is why these areas way north of us have very mild temperatures, right? You talk about people going, or you hear about people going to the beach all the time in Europe, right? But that's why. Anyway, that's just an example. Oh yeah, Iceland. I forgot I changed this. Iceland's another good example. So again, West Virginia's here, Iceland is here, right? That's really far north. But look at this. Look at the average temperatures. West Virginia average temperature in January, high of 40, low of 23. Iceland's Fahrenheit. Yeah. Iceland's average temperature is 37 and 27. Very similar, right? Iceland. Think about that. Anyway, any questions? Another good picture of how water moderates temperature, right? When you sweat, it evaporates, that cools you off. Anyway, here we go. Any questions about how water moderates temperature? All right, the next word for attendance is Indiana. Like the state of Indiana. So again, if you're online, you have to send me those words at the end of the lecture to get your extra credit points today to prove that you were present. And if you're watching the video, not the live stream, but the video later in the day, then send me a picture of something about Indiana. The Indiana state flag, state seal, state bird, I don't care. Indiana on a map, someone famous from Indiana, whatever. Any questions about how water moderates temperature? I guess, but no? Okay. Let's talk about the biological significance of ice floating. First of all, let's talk about why it floats. This water is interesting in this case. Usually when things, like I just told you, when things get colder, I've told you that the molecules move around less, right? So what happens usually when something gets colder is it gets more dense. It's moving around less. Just like if I were to blow up a balloon with my hot breath and then give it some time, especially if I put it in like a freezer, it would shrink, right? Because that air is moving around less, so it's taking up less room. Water does that too until it gets frozen. Once it gets to 0 degrees Celsius, 32 degrees Fahrenheit, then it just kind of gets rigid and it clicks into a shape. And that shape just happens to be very far apart than it usually is. Therefore, it's less dense than liquid water. Therefore, it floats. That's why ice floats. I might ask you that. But it's more important you know why that's important than how it happens. But yeah, ice floats because it's less dense than liquid water. That's the first part. Any questions about the first part? Actually, here's a good picture illustrating it, right? This is really hard for you to see. That looks blurry. Not just everything looks blurry, but in this case, that looks blurry for a reason because it's trying to illustrate the fact that those water molecules are moving around. Again, as you lower the temperature, they're moving around less, and then finally, they just kind of get to the point where they don't move around at all, for the most part, which is also pretty rare too. Usually, molecules are always moving until they get 0 degrees Kelvin. We don't talk about that, but anyway, as far as we're concerned, the water molecules pretty much stop moving at 0 degrees Celsius, and I'm not going to test you on what temperature it is, but once it gets to the freezing point, that's what happens. And then it's less dense and it floats. Any questions about that before we talk about why this is important? All right, so what happens in nature, right? Bodies of water, they freeze, right? You get ice at the top of the bodies of water. And lucky for us, that water, that ice floats because it's less dense. Otherwise, it would sink, and then things would freeze from the bottom. But what happens is you get that layer of ice on top of a lake, for example, and that's actually like a blanket. It's going to sound really weird to you. It's kind of what I talked about earlier with the orange tree things. Because you think of ice as cold, because ice is cold. But ice can be relatively warm, right? If it's negative 50 degrees in the South Pole, maybe, for example, that's cold air, right? But if the ice is only, I don't know, negative 5 degrees, it's relatively warmer, right? So it's keeping things warm, right? The ice is protecting the rest of the water to keep it from, freezing over. Therefore, life can persist, right? Which is another good independent work topic. There's very few, but there are some organisms that can survive being frozen. Actually, let me rephrase that. There's very few animals that can survive being frozen. Yeah, you can look that up for a minute if you want. What are they? If you didn't find it interesting, how do they do it? But yeah, there's other things that can survive being frozen too. But anyway, yeah, that's how it works. That's why it's important. And again, yeah, I should have told you about this at this point. But yes, they spray water on the trees. I forgot I put that on the PowerPoint. But if you download the PowerPoint, you can click that link, and it is, I think, a story. Not a video, but just a story you can read about it. Anyway, any questions about this? All right. So let's move on to the next water property, which is water is the solvent of life. And again, technically, I haven't talked to you. I guess you don't know what a solvent is because I haven't talked to you yet. But let's talk about it. First of all, you need to know what a solution is. We need to know this for this exam and then for another exam. So we're talking about solutions now. We're going to talk about them later as well. A solution is a liquid with a homogeneous mixture of two or more substances. A better way of remembering that, well, I'll tell you, once I give you all three words that you need to know, then I'll give you a better way of remembering the solution. But for now, for the next minute, know that a solution is a liquid with a homogeneous mixture, meaning it's like, for example, salt water. The salt is completely dissolved in water, and I hold up a thing of salt water. From here, could you point to me where the salt is? If it's dissolved, right? No, because that's what I mean by homogeneous, right? It's all mixed together evenly, so you can't tell one part from the other. Unlike iced tea, right? If I held up a thing of iced tea and said, hey, can you point out the ice? And you'd be like, yeah, there's the ice, there's the tea. That's not homogeneous because you can see them, right? You can see the difference. Anyway, that's a solution. The dissolving agent is called, to make the solution, is called a solvent. So there's another word you need to know. Something that dissolves something else is called a solvent. What is it dissolving? It's something called a solute. There you go. So these are words you need to know. You need to know how they're related to each other. So an easy way of remembering it is if you mix a solute into a solvent, it makes a solution. Pretty simple. Again, it's a long weekend. So you get home, and you realize your beer is warm, so you need something else to drink. Make yourself a margarita. To do that, you're going to need some simple syrup, which is water and sugar mixed together, right? So the water in that situation is the solvent. The sugar that you're dissolving in the water is the solute. And that simple syrup is your solution. Any questions about the relationship between solute, solvent, and solute? All right, technically, again, solvent is anything that's doing the dissolving. But technically, when it's water that's doing the dissolving, we call that an aqueous solution. How many of you guys have ever heard the song Aqueous Transmission? I have all of it. It's an Incubus song, not one of their hits. Anyway, any questions about this? We're still going to talk about water and its ability to dissolve things, but any questions about this particular slide? I'm going to drink my solution, water and coffee grounds.
I have a question.
Yes?
Iced tea wouldn't be a solution if water is the dissolved.
The tea itself, good question. The tea itself would be a solution. The water would be the solvent. Let me back it up. Tea itself would be a solution. Solvent would be the water. The tea leaves would be, or the molecules in the tea leaves would be the solute. They would dissolve into the water. And the solution would be tea. Now, of course, if you put ice into it, that's a whole different story. So the tea is still a solution. But when you put ice into it, that's different.
And salt water is water.
Salt water would be a solution too. Great question. So if you mix water and salt, water would be the solvent, salt would be the solute, and the salt water would be the solution. If you mix water and blue dye, for some reason you just wanted to do that, water would be your solvent, the blue dye would be your solute, and your blue water would be the solution.
What is the last word used for?
Which one? This one?
Yeah.
Oh, I'm just saying technically, again, anything, not anything, a lot of different things can be a solvent. But if it's water in particular that's doing the dissolving, we call it an aqueous solution. For example, if I take bleach and mix it with styrofoam, the styrofoam dissolves. Bleach is the solvent. Solute would be the styrofoam. Whatever mess I have left over would be the solution, right? So a lot of things can be a solvent, but when water is the solvent, it's an aqueous solution. That's actually, I'm so glad you asked, because that's actually a really important concept before I move forward. Not that I'm going to ask you about aqueous solutions, but the next point I'm about to make is it's about the fact that water is not the only solvent. But it's the only one we care about right now, right? Because this section of chapter 2 is about water. So you guys understand? When water is doing the dissolving, it's an aqueous solution. And as far as we're concerned, that's all we're pretty much going to talk about in this course, but here we go. This is why this is important for biology. Water can dissolve a variety of solutes, and it provides a medium for chemical reactions. So without water, we wouldn't be able to dissolve these solutes, and almost every chemical reaction that happens in our body would not be able to happen without that. And again, it's really good at it. There's a lot of different solvents out there. You can dissolve a lot of stuff with alcohol or, I don't know, bleach, like I already said, hydrogen peroxide. All these liquids can dissolve things, but water is really good at it because it's polar, right? It has those hydrogen bonds. And let me show you why. Well, actually, before I do that, let me ask you this. If I took my kids' Legos to class today, and I had a bunch of green Legos and red Legos, and there's one big block of them, right? They're all put together randomly, green and red. Let's say I gave it to her, and I said, all right, I want you to build me a red house, right? And I've got this big block of all these different Legos stuck together. What's the first thing she would do? Well, I'll ask you since you're listening. What would you, if I said, here's a bunch of red and green Legos stuck together, and I give it to you and said, build me a red house, what are you gonna do? You would take it apart, right? Because yeah, I gave you red Legos, but I also gave you green Legos and they're stuck together. It's useless for you. You've got to dissolve it. So just like our body needs chlorine or chloride ions, and just like it needs sodium ions, when you eat salt, you're not giving your body technically what it needs. It doesn't need sodium chloride. It needs sodium and chloride, right? So you need the water to dissolve it. And that's just one example. There's a lot of things, right? Point is, without water dissolving it, we wouldn't have the sodium or the chloride. It would just be salt, just sitting there, useless. Does that make sense? You guys, question? Okay. Anyway, let's move forward then. If there's no questions, that's the end of the water section. Are there any questions about water in general? All right, then let's move on to the next section, which is all about acids, bases, and pH. This is going to be very important for next week's lab, because we're going to do an experiment with acids, bases, and pH. It's a good time to remind you, speaking of lab. Let's see. This week's lab that we did on Wednesday is due today, Friday, sometime before midnight. And also next week's lab, the chemistry lab, is also due sometime tonight before midnight. And someone asked a question about that before most of you got here. And I'll remind you, like I said before, if you find yourself right before midnight, you're like, oh my goodness, I'm going to miss the deadline, and I haven't turned either one of them in. Prioritize next week's pre-lab over this week's lab. And more important, like we've already done the lab, so if you're a little bit late, whatever. But you definitely need to know what you're getting into next week. So prioritize your pre-lab over that. Anyway, let's jump into acids, bases, and pH. First of all, how do we define acid? And actually, does anybody know what is an acid? I would say, a lot of times, yes. I like that. That's what I was actually about to say too. Like before I had taken any of these classes, if you asked me what an acid is, I'd be like, I don't know, something that dissolves something, right? But then again, water dissolves something. Bleach dissolves stuff too, but that's actually really far from an acid. So as far as we're concerned in this class, an acid is a compound that releases hydrogen ions. And I would focus on releases hydrogen ions. That's not even the compound part. If you could just focus on, when you think acid, you should think hydrogen ions. So H+. It's an ion because it's a hydrogen, but it has more protons than electrons, right? H+. Hydrogen ions. You should associate acid with hydrogen ions. For independent work, you can look up how else you can define acid. As far as we're concerned, this is it. But there are other ways to define what an acid is, but in this course, an acid should associate with hydrogen ions. Let me ask you this. Well, no. I'm trying to think of how I can word this to where you might get it before I show you the next bullet point. If an acid is something that releases hydrogen ions, what do you think a base is? Hey, that is correct. And again, if you've answered me any questions today, if you send me the emails for extra credit, remind me that you answered some questions. Get a little bit more extra credit. Yes, a base is something that accepts those hydrogen ions. That's one way that we define base. There's going to be another way. I'll give it to you here in a second. But for now, we know that an acid is something that releases hydrogen ions, and we know that a base is something that accepts them. If we could just keep it like that, things would be very simple. But I have to make it more complicated for you. People in charge of higher education say that school has to be hard, we have to make it difficult. I made that part up, but this part is true. Come on, there we go. So, how do bases accept those hydrogen ions? As far as we're concerned, they all do this, but technically some of them do this. They release hydroxide ions, or OH minus. So again, if I were making flashcards, on one side I would have acid, get you in a second. On the other I would have hydrogen ions, H+. And then if I would have a card that said base on one end, on one side, and on the other side it would say hydroxide ions, OH minus. Yes, sir.
If acid with ions and base accepts, do they both work together?
Yes. And, oh yeah, that's up there. Yes. So look at it, right? You have an H. If you add that with an OH, you get water, right? You get H2O from that. So yeah, generally speaking, they can neutralize each other. A whole lot that goes on in chemistry for that. How strong is the acid? How strong is that solution of acid? Like, is a lot of acid in there, or is it a little bit? Same with the base. How strong is the base? What's the concentration? But here, we don't have to worry about that. Just know that hydrogen ions should be associated with acids, and hydroxide ions should be associated with bases. Good question. And that brings us to the pH scale, which is a measure, right? It's a measure of how acidic something is. You need to know that. It's a measure of the acidity. Of course, you could say it's a measure of the base, right? Because if something's really high on the pH scale, it's basic. If something's really low, it's acidic. Whatever. But this is how your book defines it. It describes the acidity, which is the measure of concentration of hydrogen ions in a solution. But the way I think of it, the way I think you should remember it, is the pH scale just tells us how acidic or basic something is. I'm going to give you some more information with that. Here we go. Here's something you definitely need to know for the exam. The lowest number is acidic, and it's 0. The highest number is 14, and that's the most basic. You need to know that. There'll be a few questions that involve knowing the pH scale. And think about all the different ways you could describe it, right? When I say something, if I say, all right, let's compare 0 to 14. 0 is more acidic than 14. That's one way of putting it. Or 0 is less basic than 14. Or 0 has more hydrogen ions than 14. Or 0 has fewer hydroxide ions than 14, right? So I just said the same thing in 4 different ways. So when you're studying this, keep that in mind, because there's no telling how I'm going to ask the question on the exam. The quiz might say something like, which one has more hydrogen ions, this or that? But then the exam might say, which one has more hydroxide ions, this or that? So keep that in mind when you're studying this. Any questions about this slide? Yes, ma'am.
The lower the number, the more hydrogen acid.
Yep.
Right?
Hydrogen ions, yep.
Okay.
And if you remembered it that way, you'd be okay. Technically, it's a hydrogen ion, but saying hydrogen is not going to hurt you. I'm not going to trick you on the exam, so on the multiple choice, for the choices, you're not going to have to choose between hydrogen or hydrogen ion. It's too tricky. It's a 100 level class. But yeah, technically there's a difference, right? A hydrogen ion is not technically a hydrogen, it's a hydrogen ion. it's giving up an electron, it's positive, but yeah. So yes, if you remember, the lower something is, the more hydrogen ions it has, that would work. Or the lower something is, the fewer hydroxide ions it has. It's really confusing in a way. And you could look it up if you want. It might confuse you though, like how we get the pH scale. It's a lot of math involved. It's not intuitive. Like when you think about it, if we're saying something that's really acidic, wouldn't that make more sense to have a higher number? But it's not the way it works. It's a negative logarithm. So unless you're into math, maybe you shouldn't look it up because it could be confusing. So just know, again, very low number is acidic, very high number is basic. All right, another thing you need to know, this is where people usually screw it up, is that when we're talking about the pH scale from 0 to 14, for every step is a times 10 change in concentration. So 0 to 1, 1 is 10 times less, how do I put that? Yeah, 1 is 10 times more basic than 0. 2 is 100 times more basic than 0, right? Because you go 10 times 10. Right? 3 is 1,000 times more basic than 0. 4 is 10,000 times more basic than 0. So every time you move, you multiply it by 10. Again, complicated stuff, right? The math behind this can get confusing. Sort of like the Richter scale. Is it Richter scale? Yeah, for earthquakes, it's a multiple of 10 for each number. Anyway, any questions about this slide? We're going to yeah, the next slide I'm going to show you will illustrate what I'm saying here. The next two slides. First is this. Again, if something is really basic, it's got more OH ions than H plus ions. It's more acidic, it's got more of those H plus ions. And of course, if it's neutral, it has about equal amounts. Any questions about that picture? All right, here's where it gets a little bit trickier. This is what you need to know. You do not need to memorize any of this. I'm not going to ask you, like on the exam, I'm like, what's the pH of human blood? You don't need to know that it's 7.4. You don't need to memorize any of this. But on the exam, and then even in the quiz, I might give you this picture as a point of reference and say, how much more basic is urine than grapefruit juice? Urine and grapefruit juice, right? So, all right, we can see that urine is more basic than grapefruit juice. We know that. How many steps? So 1, 2, 3. So that's 10 times, 100 times, 1,000 times. Urine is 1,000 times more basic than grapefruit juice. Another way of saying that, grapefruit juice is 1,000 times more acidic than urine. Grapefruit juice has 1,000 times more H plus ions than urine. Grapefruit juice has 1,000 times fewer OH ions than urine, right? All the different ways that I could ask that. That's what I'm saying for the exam. When you're studying this, think about all the different ways you could describe the same thing. And if you get stressed about it, don't worry. There'll be like one question on the exam about this. So again, if you're looking at this, you're like, I can't get it. Don't worry about it. It's just one question. Anyway, any questions about this picture? All right. Yeah, I like this picture. This is something I found on the internet, so I shared it with you. There's actually a whole page on Facebook dedicated to this. It's called Dihydrogen Monoxide Awareness. So this was meant as a joke, but it's a great illustration of how people try to scare you by telling you the truth in a scary way. Dihydrogen monoxide is water, by the way. Dihydrogen, 2 hydrogens. Monoxide, 1 oxygen, right? One oxygen, 2 hydrogens. That's water. Dihydrogen monoxide is an acid with a pH level of 7. You could say it's an acid. Technically, it's an acid compared to bleach with a pH level of 10, right? So you could call it an acid because it's right there in the middle. And that's the highest pH level than any other acid, right? Because anything above 7 technically would be basic. So again, it's telling you the truth, but it's trying to sound scary. And I know it's a joke, but people really do things like this trying to scare you. But it's the truth, right? It's trying to set it in a scary way. Yeah, good example. Anyway, any questions? Let me go back one slide. Let me ask you this. And I'm really thinking about margaritas a lot. But anyway, lemon juice, pH level of 2. Same with lime juice. How many of you ever drank lemon juice or lime juice in something. All right. How many of you ever drank tomato juice? A Bloody Mary. Okay. How many of you have ever drank coffee? Good. Urine? Good. You guys haven't had to drink urine yet. You're doing good. How about battery acid? Good. No one's drank battery acid. Anyway, the point is, how many of you, after drinking lemon juice or grapefruit juice or tomato juice or coffee, or soda, how many of you died after that? No one? Amazing, right? But look, pure blood, or your blood, is a pH of 7.4. It's almost neutral. And if it gets too far high or low, like if it gets too acidic or too basic, then you die, right? And you can look that up for independent work too. How high is too high? How low is too low? You can look that up for independent work. But why is it that when we drink all these acidic things, we don't die, right? And the answer is buffers. Buffers are substances that minimize the change in pH. You need to know that for the exam. You need to know that for next week's lab. Buffers are substances that minimize changes in pH. The next word for attendance is fatty, F-A-T-T-Y. So for you guys, you can just send me the word fatty. For those of you watching the live stream, you can just send me the word fatty. For those of you watching the video, I don't know what you're going to do. It's fine. Send me a picture of fatty. Curious to see what you'll come up with for that. Don't send a picture of me sensitive about my weight. I haven't had a chance to work out anymore. Kids are killing me slowly. Any questions about buffers? All right. Next one, we talk about biological molecules. We're not going to see you again until Wednesday. Let's just end 3 minutes early because we don't have time to jump into the third and final portion of this chapter. So I'll see you guys on Wednesday. And yeah, which is I should remind you too, since she asked me to bring up the last slide. You guys have access to these PowerPoints. So if you go to WBSU Online, scroll down, you'll see all these PowerPoints are there. And if you download them, that makes them yours. So you can even adjust them and edit them, do whatever you want. You guys have a good weekend. Stay safe. Have fun with me, because I will not be having fun. Yes.
So one thing that we were having, it was on an actual Excel chart.
Yep.
This right here. How do you want to do it?
You don't need to. Yeah.
Oh.
It's already. I have access to it because it's a Google Doc. So all you need to do is that one question under that link. It says, "Did you do the extra credit?" Just put in yes, and then I'll fill out the link above. Good question.
Because I forgot to type in yes or no because of.
Well, I can still do it. So you're saying you did it, and I just didn't give you the extra credit?
Yeah.
Perfect. Yeah. So
Okay.
I guess either resubmit it or send me an email reminding me what you just told me, and then I'll adjust it.
Okay. So I'll just do it right now since I'm here.
Sure. Yeah.
I have the chart.